This lesson is on regular polygons. Let's recall what a regular polygon is. That's one that has all of the side lengths the same and all of the angles the same. The first one that we dealt with would have been a triangle. You recall that a regular triangle or an equilateral triangle can be inscribed into a circle. Remember also that all triangles can be inscribed in a circle. That's the circumcenter theorem. By the way, inscribed in a circle means that a circle can be drawn through each of the vertices. All triangles can be circumscribed. That's the circumcenter theorem. That what we did triangles. We'll do let's see, a regular quadrilateral is a square, of course. A square can also be circumscribed. All of the vertices can be on a circle. There are other rectangles and other quadrilaterals that can be circumscribed, but all cannot. Like triangles, all can. All quadrilaterals cannot. A pentagon. If I have a regular pentagon, it can be inscribed. A circle can be drawn around it such that each of the vertices are on the circle. A little bit more terminology. Oh, first off, all triangles can be circumscribed. All regular polygons can be circumscribed. There are other polygons that can also be circumscribed and some that cannot. We'll talk about the center of the circle that circumscribes the polygon as the center of the polygon, the regular polygon. We can draw radii of the circle out from the center. These radii will, of course, all be congruent. For the circle, we call them radii, but we're going to go ahead and also call them radii relative to the polygon. The point that's in the center of the circle will be the center of the polygon, the regular polygon. Those are all circle terminologies, and also another circle terminology is the central angle. That's the angle that's at the center of the circle and at the center of the polygon. So here this one would be 360 divided by 3, 120, 360 divided by 4, 90, 360 divided by 5, 72 degrees. Those are all the same as the circle terminology. We add a new one with polygons, and that's the apothem. The apothem is the perpendicular distance from the center to the side of the polygon. Notice that this forms an isosceles triangle since two sides are radii, the third being the side of the polygon. The two sides that are radii are the same length, therefore it's isosceles. Recall that in an isosceles triangle, an altitude dropped from the vertex to the opposite side bisects the angle, which means that this angle is, the big one's bisected, so this is half of 72, which is 36 degrees, which will be true in a similar course for the others. This is written down pretty for you here, so you can read it. And here's what it looks like in a picture with an octagon. We'll use this octagon to try to figure out how we can find the area of any regular polygon. Notice that the black around the outside is the perimeter of the polygon. I have some already cut up pieces representing the slices here. I'm going to go ahead and put them in. Here we have our octagon. I'm going to take all of the octagon, cut into these pie shapes, and I'm going to see what at first, I'm going to see how I can find area. First, remember what we did from last time, and that is that all area is basically a unit square. 1 by 1, a unit square. the way we do finding the area of shapes is we make it into a rectangle and then slice it vertically, slice it horizontally until we get unit squares. Then we count the unit squares, slice, slice, count, and that way we know the area of it. So if this were only a rectangle, we could do it. Let's take the pieces, see what happens. So I'm putting them together, I'm rearranging them in this shape. And we'll see pretty quickly that they make a rectangle. Some observations about this rectangle. The dark black line, the top and the bottom, was the perimeter of the original octagon. There are two equal pieces, so one length here is half of the perimeter of the original octagon. Notice that relative to the square, to the rectangle, it's the length of the rectangle. So we're getting close to being able to do the area. We just need to know the width of the area. And we look here and we see, oh my, the width of the rectangle is the same as the apothem of the polygon. So what do we have here? We have that perimeter, perimeter, half of perimeter is the length of the rectangle. The apothem is the width of the rectangle. Therefore, it looks a whole lot like we've got a theorem. And indeed we do. The area of a regular polygon. The area of a regular polygon is 1/2 times the apothem times the perimeter. A usage note here. Frequently but not always, in formulas, small letters represent measurements and large letters, uppercase letters, represents things that are calculated, like the area or the perimeter, and then the measurement would be the apothem. We're going to do a few things with this. And let me remind you of your special right triangles. The special right triangle, we have the isosceles right triangle, where we have an isosceles triangle. We know that the value of the short side times the square root of 2 is the hypotenuse. In a 30, 60, 90 right triangle, we know that the short side times 2 is the hypotenuse, and x times the square root of 3 is the middle size. I remember, but x is the little one, 2x is the big one, and square root of 3 is between x and 2x. So it's between, and it's the middle. Remember, some of this you'll be needing to use trig. Remember, SOHCAHTOA, and to make sure your calculator is on degrees and not on radians. Our first one, we'll do an equilateral triangle. Here I have an equilateral triangle. I'm going to go ahead and draw my center. I'll draw the radii. Notice that the central angle is 360 divided by 3, which is 120. I'll draw the apothem. Perpendicular distance from the center to the side. And for this particular problem, I'm going to give you that the apothem's measure is 3. Now we need to figure out the perimeter and the area of the triangle. Okay, well, this is bisected because it's the altitude of an isosceles triangle. So the angle is bisected and it would be 60. The other unknown would be 30. So we have a 30-60 right triangle. Remember that you can find the side length by using the small, then the medium is the small times the square root of 3. So it would be 3 times the square root of 3. And our calculations for this would be given here. small side of the medium side of the small triangle is 3 times the square root of 3. So then you can say, well, the side length of the entire equilateral triangle is 6 times the square root of 3. There are 3 of them, so 18 times the square root of 3 would be the perimeter. Then to find the area, we'll do the theorem that we just noticed or demonstrated. That is half of the apothem times the perimeter. A half of 3 is the apothem, and the perimeter is 18 times the square root of 3. Simplify it out, you get 27 times the square root of 3. It's a good thing if you would draw these as with me as I'm going, pause as you need to, of course. Here is a regular quadrilateral, which is inscribed into a circle. Its vertices are all on the circle. Of course, it's a square. I'll draw the radii, which in this case are diameter as well, since it's 4. Central angle is 90. I'll draw the apothem. And what we know about this one is that the radius of the circle, the radius of the figure, is 10 units. So go ahead and figure out what this will be. Notice a hint here. The big triangle inside of the square is isosceles, but this small one is also isosceles. So that means this is a 45, 45, 90, an isosceles right triangle. And the shortcut will apply. Okay, here's what you should have gotten for the square. And there's lots of ways to do a square. Working it according to the method that we've been using here, being consistent with that, I've worked it according to the formula. I've used special right triangles to find out that the side length is 5 times the square root of 2. This was the hypotenuse. The hypotenuse is the side times the square root of 2. Hypotenuse is the side times the square root of 2. Then I simplified and rationalized the denominator to find out that the side length of the shorter, smaller triangle is 5 times the square root of 2. I can then either say there are 8 halves and multiply by 8, or I can say that the side length of the square is 10 times the square root of 3 times 4 sides. In either event, I'm going to get the perimeter is 40 times the square root of 2. Then I can go ahead and do the area. The area will be 1/2 of the apothem times the perimeter, or 200. This can also be done as a rhombus by doing the diameters. This is probably the easiest way to do this one. Since we have that the radius is 10, we can double it to be 20 and multiply. We can also work it as a square, which, if we have the right side, is the easiest way. Our next one will be the regular pentagon. Do the same thing here. We'll start with the center of the pentagon, draw the radii. The central angle is 360 divided by 5, which is 72 degrees. We'll draw in the apothem. Notice again that this forms an isosceles triangle, that this is an altitude of the triangle, and that therefore the angle inside the small triangle is 36 degrees. For this exercise, I'll give you that the apothem is 6. So please pause it and figure the perimeter and area of the polygon. Pentagon this time. Okay, here's what you should have gotten for the pentagon. We're going to have to use trigonometry because we don't have any special right triangles to help us out with a shortcut. The side that we need is the portion of the side length of the pentagon, the regular pentagon. So that's what we need. We know 6. We know this angle, so this angle, opposite is x, adjacent to it is 6. That's tangent. So we go ahead and work it as tangent. I rounded to 1 decimal place here. Find out again that the side length is 10 times, because there are 10 halves, 4.4, which is 44. Now I probably shouldn't have rounded so little, and I'm now working with a rounded number, which I'm not really supposed to do, but I'll do it for the moment, and that's going to get worse when I do the next one here. Half of the apothem times the perimeter would be the area, and that simplifies to 132 with a little bit of forbidden intermediate rounding. Our next one is the regular hexagon. I'll go ahead and draw the radii of the hexagon and the circle that circumscribes it. Not only is this one isosceles, but it's actually equilateral. How do I know that? Well, 360 divided by 60 is 60 degrees for the central angle. I know that it's isosceles, therefore the base angles are equal, therefore what's left for them is 180 minus 60, 120, divided by 2, which is 60 degrees. So these are equilateral. I'll go ahead and draw the apothem. Notice that again, this is half of the central angle, or 30. Now this is my 60. I have special right triangles again. Probably the best way to work this is for a simplicity. So go ahead and pause it, give it a try, find the area and the perimeter of this polygon. The side length of the small triangle is 2 times the square root of 3. At this point, I can either go with the 2 times the square root of 3 and say there are 12 half sections, or I can go with the side length of 4 times the square root of 3 and say there are 6 sides. Either way, I'm going to get 24 times the square root of 3. I substituted into the formula for area 1/2 the apothem times the perimeter, and I get 72 times the square root of 3 is the area of the triangle. Is the area of the hexagon. The next thing to do is this. An equilateral triangle is shown inside a square, inside a regular pentagon, inside a regular hexagon. Write an expression that says the exact area of the shaded regions. Then approximate the area of the entire shaded region, rounded to the nearest whole unit. So if you would, pause and give this a go in your cipher. Here's how it works out. So that you can see how it works. I've done for each of the shapes and then added, subtracted the shapes to get what I need. I've put here some common errors. So if you get the wrong number down here, this may be the error that you made so that you can go back and find out what you've done. And here ended the lesson.